In this screencast, I'm going to show you how to solve transient conduction problems using the lumped capacitance method. So transient conditions occur when boundary conditions change. For example, let's say we have a solid that's at some temperature, T sub S, and it's placed in a thermal environment that's at T infinity, a bulk temperature that does not equal our T sub S. The temperature within the solid will continue to change until the system reaches steady state again. The governing parameter for transient conduction is known as the Biot number. And this is defined as the convective heat transfer coefficient times the characteristic length of the solid divided by the thermal conductivity of the solid. So this characteristic length is often calculated by taking the volume divided by the surface area of the solid. So for a plane wall, that would be L. For an infinite cylinder, that would be the radius divided by 2. And for a sphere, that would be R over 3. However, there's a more conservative approach that defines the characteristic length as the length associated with the maximum spatial temperature difference, which would still be L for a plane wall, but radius for both cylinder and sphere. The easiest method to use to solve for the time that takes to achieve steady state is lumped capacitance. And here we assume that the temperature of the solid is spatially uniform at any given time. So that means that the temperature is a function of time, but not position. Therefore, the lumped capacitance method allows us to solve for time as equal to the density of the solid times its volume times its heat capacity divided by the convective heat transfer coefficient times the surface area of the solid. And this is all multiplied by the temperature difference term, the natural log of theta sub I over theta sub 0, where theta sub I is equal to the initial temperature of the solid minus this bulk temperature, and the theta sub 0 is equal to the centerline temperature of the solid minus our T infinity. So in order to use lumped capacitance, our Biot number needs to be less than 0.1. Therefore, for any transient problem, the first thing you need to do is calculate that number. So what we're going to do is we're going to look at a sphere, silver, and its temperature is 400 K. It has a diameter equal to 50 millimeters, and its thermal conductivity is equal to 420 watts per meter K. And this is going to be placed in a water bath with a temperature equaling 290 K, with a convective heat transfer coefficient of 1500 watts per meter K. And what we want to know is how long does it take for the centerline temperature to equal 310 Kelvin. So let's calculate that Biot number. So that's going to be equal to our 1500 watts per meter Kelvin. And we're going to use the more conservative approach and multiply that by our radius. And we divide this by the thermal conductivity of the silver. And when we calculate this, our Biot number is 0.089, which is less than that 0.1 that we need in order to use our lumped capacitance. And as we showed before, The volume divided by the surface area is equal to R over 3. So the density of silver is equal to 10,490 kilograms per meter cubed. And the heat capacity is equal to 230 joules per kilogram Kelvin. So let's put these numbers in. The left-hand part of that term is equal to 13.4 seconds. Now let's calculate that temperature part. So the natural log of 110 over 20 is equal to 1.7. Therefore, our time is 13.4 seconds times 1.7, which is equal to 22.8 seconds. The time it takes for the centerline temperature of a silver sphere that's at 400 K to reach 310 K when placed in a water bath at 290 K is equal to that 22.8 seconds. In a subsequent screencast, I'll show you how to solve the same problem using a more accurate analytical method so we can compare the suitability of using lumped capacitance for this situation.